Hello everyone, welcome back to the fifth video of my graph data structure series. In this video, I'm going to cover how Bellman-Ford algorithm works. So in our previous video, we saw how Dijkstra's algorithm works and how it is very important to find out the shortest path between two nodes. Now you will be asking yourself, then why do we need Bellman-Ford algorithm? Let me tell you something. For example, let's say you are going through a network of road. Okay, so you want to go from source to destination. So we can we can define the toll tax values that we're going to give as a weight in this case, right? So the problem with Dijkstra's algorithm is that it doesn't deal with the negative weight values, right? So in this case, if we have any negative toll values, that means if we have any sort of discount in our toll tax, it is not going to process. Dijkstra's algorithm is not going to process, and it is not going to show us the shortest path or most optimal path because it is not able to process that negative weight value. So that is where Bellman-Ford algorithm comes into the place, because it deals with the negative weight values. And if it is able to deal with negative weight values, if it is able to deal with the negative toll tax values, that means we are able to process the discount in our route. So that is how we will get the most optimal route in the case of negative values, right? So unlike the Dijkstra's algorithm, it doesn't use priority queue for efficiency or anything like that. It actually uses more systematic way of iterating over all the edges one by one, and it finds out the shortest path available, including negative weights. But the thing is that the Dijkstra's algorithm is relatively faster than Bellman-Ford algorithm, but it doesn't deal with the negative weight values. So in order to process all the negative weight values, we would need Bellman-Ford algorithm. So let's understand first how Bellman-Ford algorithm works. And then after we will understand it, we will implement that Bellman-Ford algorithm into our code. So let's get started. All right, so first of all, let's go through the example now and let's understand how Bellman-Ford algorithm works. So as you can see, I have example over here one. So we have three vertexes here, 1, 0, and 2. No, and we have basically three elements, and we have edges created over here. So edges are 0, 1, 5, 1, 0, 3, 0, 1, 5, 1, 0, 3, 1, 2, -1, and 2, 0, 1. The reason why I chose this example because it feels like it's a great mixture because it also involves negative weights here, -1. So now we will be able to determine how is it beneficial to use Bellman-Ford algorithm with the negative weights, and we can also then detect if this graph has negative weight cycle or not. Okay, so basically, if we want to see how much distance it takes to reach V, okay, so how much distance it takes to reach V. So it's basically going to be U plus V, U plus weight, sorry. So let's say I want to go here from 1 to 0, right? So in this graph, let's say I want to go from 1 to 0. So weight is 3, and then I'm going to add up 1 plus 3, and then I'm going to check 4. So I'm going to check if 4 is lesser than the existing distance or not. Okay, so if it is lesser than existing distance, that means we have found a shorter distance, and then we can update that distance in our distance array. So first of all, we will start with source is equals to 2. So that means we will put 0 in our second index of a distance array, and then we will put all the other elements as infinity. As you can see, this is our distance array. This is a distance array, so infinity, infinity, and 0. So now here, so we have to do n minus 1 iterations. N minus 1 iterations, as you can see, we have n is equals to 3. So we are just going to do 2 iterations here. I'm going to tell you why we actually need n minus 1 iterations only, and why we don't need to go any step further than n minus 1 to find out the shorter distance. So let's start from here first. Okay, so distance at 0 plus 1. Okay, so distance at 0. What is the distance at 0? It is infinity. Distance array at infinity. So we will move forward because we will not be able to do anything with this. Even distance at 1 plus 0, this is also infinity. Distance 1 plus 2 is infinity. Now here we are, distance 2 plus 0. Okay, so distance at 2 is basically what? Uh, its distance at 2 is basically 0. Okay, and then sorry, here it's 1 because our weight is what? 1. Okay, so 0 plus 1 is equals to 1. So now we are going to check our distance with the existing value. So that means we are going to check our 1 with what we have right now at 0. So what do we have right now at 0? We have infinity. So obviously 1 is greater than infinity. So now we will update this infinity with what? 1. Okay, so we have 1, infinity, and 0. This is going to be our new distance array. And then we will move with our second iteration now. So if you can see here, sorry, the weight here is 5. Sorry, weight here is 5. Here it's 3. I've actually messed up here while writing the values. So here it is supposed to be weight. Weight is supposed to be here because distance at u plus weight should be lesser than distance at v. So u is source, weight is obviously uh, the one that we have in our graph, and then distance v is destination that we are going to reach from source. Okay, so now let's check again. So 0, what is 0? 1 plus 5 is equal to 6. So now we are going to check 6 with what? Distance at 1. So we are going to check if 6 is greater than what we have, is lesser than what we have at distance of 1. So we have infinity right now. So we will check this off and we will put here 6. Okay. Then we will move one step forward and then we will go to distance at 1. Okay. So distance at 1 is what? 1. 1 plus 3, 1 plus 3 is going to be equal to 4, but we already have, so we have 4 here and we already have 0. So it is not satisfying this condition. That means it's not a shorter distance. So that means we are just going to keep 0 here. We are not going to update anything. Okay, so that's how we will reach to the conclusion. We will also do the same iterations with the rest of our cases, and we will reach to the conclusion that our shorter distance from the source is going to be 1, 6, and 0. Okay. So this is for index 0, this is for 1, and this is for 2. So that is what we have right now. Okay, perfect. All right, so now as we have gotten our shortest distance, now our next question is, why do we need n minus 1 iteration? What's the reason behind that? So let me tell you this. So if we look at this iterations, if we look at this dry run of if we look at the dry run of this particular example, so we got distance at 0 from distance 1, sorry, from distance 2 in first iteration, and then we got distance of 1 from distance of 0 in the second iteration. Okay, that means as long as we are keep doing the iterations till n minus 1, we will keep finding shorter distance for some of the cases, right? Because we got distance at 0 from distance at 2, and then we got 1 from 0. So all of them are some sort of connected, and that is helping us to determine and update the shorter distance for this particular destination, right? So that means we only need n minus 1 iterations, because if we have only 3 elements, then I'll probably get 3 from 0, I'll probably get 3 from 1, and then from 2 from 0, or 2 from 1. So that's how it will keep running on until n minus 1. So we don't need to really go further than n minus 1, because we will be exploring all of our cases by then. Okay, and then one more case is that if we want to know if our graph has a negative weight cycle or not, we just have to move one step forward. That means we have to do our nth iteration. That means we have to do nth iteration, because the shortest path distance algorithm will be good until n minus 1. And if we do nth iteration, and if we still found out that, okay, I have one more shorter distance value of some of the destination, that means there's something fishy, and then that means that the graph has negative weight cycle, because because this algorithm is not supposed to update any shorter distance after n minus one iteration. So if we go to nth iteration, and if we found out that I have one more shorter value for the distance, that means it has a negative weight cycle, and then we have to stop right there and we have to return basically minus one in our algorithm. So that's how it basically works. That's how Bellman-Ford algorithm works. It might look complicated right now in this, because also it's my fault. I mean, it's kind of messy as well. But let's look at the code. Let's look at how it works, and then I'm sure we will get some better idea of how this particular algorithm works. So let's get into the code. Okay, so perfect. Now, as we have understood how this thing works, let's try to implement it in our code. So as we have discussed already, we need a distance array here, and initially our source is going to be defined or initialized as 0, and anything other than that should be declared as infinity. Okay, so let's define our distances array here. So we are going to give it name distances, and then we will have to give it a size v. Okay, now we will also have to define infinity here, because as we have discussed, we need to initialized initialize each and everything with infinity first. Just we just need to keep the source 0. All the values needs to be infinity. Okay, and then let's run a for loop so that we can fill up all our values with infinity. Okay, so it is just a very, very simple and basic thing. Distances I is equals to infinity. Okay, perfect. So far, so good. Now, next thing we need to do is we need to initialize our source is equals to 0. Okay. So now next step. So we will say this is step 2. So next step 2 is going to be the very, very important step. I would say this is the most crucial step in this algorithm, and that is to relax all the edges. By relaxing all the edges, I mean we'll have to find out the shortest distance between the source and destination using this step. Okay, so first of all, as we have discussed, we are going to do v minus 1 iterations. So I is equals to 0, and then we will iterate this for v minus 1 times. Okay, and then I plus plus. Okay, now we will have to go through all of our edges, and then we have to check if the weight that we have already have is shorter than we have, or sorry, the weight that we already have is short enough or not. Okay, so let's go through each of our edges, right? So each of our edges, and okay, so my source, so let's say we are calling source as u. Okay, so that will be edge 0. That will be the first element of my edge. And then destination, that will be the second element of my edge. And then the weight, which will be the third element of my edge. Okay, so now we have done this. Now we just need our proper if statement, um, which will determine if the distance is short enough or not. Okay, so it is going to check distances u plus weight is less than distances v. Okay, so we have already discussed all of this logic in whiteboard, so that's why I'm just writing here without explaining. Okay, so distance u plus weight. Okay, that's perfect. Now the next thing we need to do is we need to define step 2 now. Okay, so step 2, what is step 2? Step 2 is to remove negative weight cycles. Okay, so if a negative weight cycle exists, return an array with -1. Okay, so how are we going to determine that we only have a negative weight cycle? So look, as we have discussed, we are doing n-1 iterations. Okay, n-1 iterations in order to find out the shortest path. In order to determine, in order to determine if it has a negative weight cycle or not, we will do one more iteration. That means we will go for nth iteration, and still we are able to find out the shortest path for any of our elements or for any of our nodes. That means it has a negative weight cycle, because it should not find a shortest path after n minus 1 iteration. So we will do one more iteration, which will be technically our nth iteration. Okay, so we will do this, and then we are going to do the same thing here. Okay, so I'm just going to copy paste this, but instead of updating my shortest path here, I'm just going to return an empty array. Okay, I'm just going to return an not an empty array, but an array which consists of -1. Okay, perfect. So that looks good. Now the last check I will say is that we can just check the unreachable vertices. Okay, so unreachable vertices. That means the vertices that are not reachable, we will just go and iterate it, v plus plus, and then distances of I is equal to infinity. Okay, wait, if distance of I is infinity. Okay, so that means if we are still determining an infinity value in our graph, that means that point is not reachable at all, because we haven't updated that value yet. That means it's not reachable, and then we will have to keep it as it is. And then later on, I will have to uh, just return the distances array. Let's try to compile this program and see if it works or not. So it is getting compiled, it's buffering. Let's see if it works. So compilation is completed. This test case has been passed, but we still need to submit if we want to check all of our test cases are getting passed or not. Okay, so let's see. Um, yeah, here we go. So all the test cases are passed. That means our implementation was correct. And I think that was everything about Bellman-Ford algorithm. This is how we can use Bellman-Ford algorithm to handle negative weight values. So I think that's it. So thank you so much for watching, and see you till the next video.